For our last capacitor demo, we're going to look at a set of parallel plate capacitors. Don't forget, we have two metal plates separated by an insulator. And for these, we can change the distance between the plates. So let's see what changing that distance, what kind of effect that has on our system. So for a parallel plate capacitor, we can define the capacitance in terms of this formula. In this case, C is the capacitance. Kappa is the dielectric constant, and that depends on the material you have. In our case, it's air. Epsilon naught is the permittivity of free space. A is the area of our capacitor plates, and D is the distance between them. So we can see that if we change the distance between the plates without changing the shape or the area of our plates, our capacitance is going to change because we're changing this D, right? And that change in capacitance is going to have an effect on the charge. So how can we demonstrate it? Well, let's do this quick demo. In this demo, we're going to use a Van der Graaf generator to produce a voltage that's going to charge our capacitor, and we're going to look at the charge on the capacitor using the electroscope. Now, the greater the charge, the more of an angle between these plates we're going to see, right? So I'm going to start charging up the capacitor. Now, we're starting with our plates separated really far. Let's see what happens as I move the plates closer. Take a note of the distance, the angle between those two. So I'm going to start moving the plates closer together. Now we see as the plates get closer together, we're getting more and more charge. This should make sense because if we look at our formula, as the plates are closer together, D gets smaller, therefore capacitance goes up. If the capacitance goes up and our voltage is staying constant, the charge should go up as well.